Amazing presentation, I know, by Pranav. I don't think Pranav needs any introduction. Anyone who has been following your AI space should be knowing Pranav. If you don't know Pranav, then you're not following radiology AI space well enough. He's a very dear friend, and I think one of Pranav's early work in the chest X-ray space has been very transformational for the entire ecosystem. After his work, phenomenal work on the chest X-ray, we saw this big wave of chest X-ray AI companies coming out. I think last known there are 25 companies doing chest X-ray AI. All probably started with this work. Now he has moved on the domain and the modality has moved on to the abdomen space, and I think he has something that we have not seen before. I have not seen before. So before much ado, I'll the other mic to Pranav to talk about his work, both in the academia and now he has his own startup. And I hope he's also going to talk about what are his visions and plans for his startup too. What do you, Pranav?
Thank you for the very kind introduction and delighted to be here. So I'm going to press next on in here. If you can see different, I think I'm going to have to click. So I want to talk about just a couple of things here. One is the kind of vision that we're working towards, and then some progress as part of the company a2z. I've thought about this space of radiology AI as solving two fundamental questions. One is how can we match the diagnostic capabilities of expert AI, and then how can we augment the expert capabilities? It's sort of this world of acute robot joining in the search for all the diagnostics. And we're in the age of what I think are as narrow specialized solutions, where we have solutions that can detect one disease from one modality really well. And that's great, but it's very different from the value proposition of what we expect from doctors, which is we expect comprehensiveness in reporting, and we expect context-drivenness in the reporting. So with narrow AI, we're only representing a subset of this space. And the vision here is over the next 10 years, how can we build these generalist medical AI models that can do everything that doctors can do and more? And so generalist medical AI, the way we define it, is AI models that can tackle the full spectrum of tasks that doctors can do and more. I just want to define a little bit of a framework of what this means, and then some concrete examples of how we built it. I'm really okay. I can just use this. So we talked about this idea of generalist medical AI in a Nature publication in 2023, where we defined three key capabilities of GMI. Thank you. One is dynamic task specification, second is multimodal inputs, and third is multimodal outputs. And I'll just define what each of these mean. When we have an AI algorithm that's deployed today, we expect it to do what it was trained to do. For example, from this brain MRI output, what is the likelihood of there being a mass? But what I mean by dynamic task specification is our ability to ask a model questions like, is this mass more likely to be a tumor or an abscess? And have the model be able to respond with an answer that looks like that. The idea of multimodal inputs is the ability to take in imaging and non-imaging information and be able to take that all into account into making a assessment here of rheumatoid arthritis. There are many, many areas within and outside of imaging where multimodal AI will and is making a difference. And one of the less talked about ideas is not about multimodal inputs, but about multimodal outputs, which is how can we have both a natural language output, but an explanation of that with pointers to the image saying, this is the reason for my assessment. And so we started working on this last year within my academic context in a model called Adversa, where it was asking the question, can we have a single model that was trained on many different kinds of images, including X-rays, CTs, fundus photos, GI images, and be able to tackle all these different kinds of tasks together. And what we showed was that on 9 public benchmarks, we were able to set the state of the art on tasks, including chest x-ray report generation or medical image classification for skin lesions, or do it for even 3D modalities and detect anatomies. So I want to share with you a demo here of this MedVersa model. So you can upload an image, and often you can type in context to be able to say what's the clinical background and the indication, and also ask specific questions like, here, does the patient have pulmonary edema? Be able to look at skin lesions and be able to make detections off of that. Things like doing segmentations also on top of the image, or take in a head CT or brain MR and ask questions that are relevant about the image. And the question is, how do we make this validated in practice? How do we validate such tools? And one of the things we've proposed for that is ask experts to decide which one of 2 reports is better, where one of them has been written by AI and another one has been written by an expert, and it's blinded to the source. And what we find is that in 71% of cases, there's equivalence in whether or not there was a preference for an AI-generated report or a human-generated one. But what we are trying to measure, what a lot of us are working towards, is productivity and efficiency gains for the expert. And so we measured this in an experiment where we said, let's provide these draft reports and let's see how much time is saved. And this is the first study actually to show the effectiveness of AI report drafting in terms of being able to improve or show improvement on, in this case, 10 radiologists, 10 out of 10, that we performed this experiment with. And a lot of people make comparisons to GPT-4b, asking, how well does that do? It takes more time as a result of using GPT-4b to draft a report than to just use a normal negative template. And so this is a very clear indication of, if you use a bad model, you actually hurt the radiologist's productivity and rather than help. One of the things we also care about is what is the error rate. And what we find is that with these draft reports produced by MedVersa, we're able to reduce the discrepancies between different radiologists. And this is ultimately what we want to achieve. So currently, on generating reports from chest x-rays, MedVersa is currently the best model, and it's a public leaderboard called the RexRank leaderboard. And there are vendors around here that are submitting to be part of this leaderboard, and we need measures like these to be able to evaluate how well report generation models do. Skip over this demo here and just say that models like MedVersa or Microsoft's Mera 2 are doing pretty well compared to models like GPT-4b on these tasks, and a big gap. So what I want to talk about next is the work that we're doing in the company called a2z Radiology AI, where we set out to ask the question, could we build best state-of-the-art model, starting with Abdomen-Pelvis CTs and expanding to various complex modalities. For Abdomen-Pelvis CTs, because it's traditionally been considered a very, very challenging problem for AI, and certainly is in terms of training for people. And so in October, we launched a2z1, which could do 21 actionable and acute findings. And in November, we launched a2z2, which is a 140 findings model that I'm going to show you as well. Currently, the model is pre-FDA clearance, so it's available for research use and clinical trials. So a2z1 was really focused around asking the question, for acute and actionable findings, how well could we do? And in particular, how well could we do on unseen data from sites and health systems whose data hadn't been part of training? And so we did this experiment where we achieved an AUC of 0.922 across these 21 findings on data from 2 external institutions. These are the 21 findings. We cover both acute findings and chronic findings that might encourage further care for the patients. One of the most important questions that comes up on validation is how will things change when we have a different patient population or a different scanner? And one of the ways we can predict that is to be able to say, how does the model perform across different subgroups? One of the most important subgroups is age and sex on the patient side. And on the imaging side, with Abdomen-Pelvis CTs, we can often think about body part decomposition as something abdomen only, abdomen pelvis, chest abdomen pelvis, pelvis only. And so we have that breakdown here, as well as doing different types of contrast. So like solutions which only look at non-contrast CTs or venous space CTs, model performs well across different kinds of contrast and contrast phases. And in terms of scanner manufacturers, we generally see a consistency in performance, but with some room for improvement on the extreme low cases of scanners. So we tested this model on large-scale validations across 3 health systems, and these are practices that represent data from 3 U.S. States, which are both in urban and rural settings. What we found was consistent performance across these 21 pathologies, showing that the model can, in fact, have robust performance across different settings. Of course, AUC is not the only metric of interest for us. We also care about what happens when you pick a threshold and decide to apply the model on new cases. And here, one of the decisions we made is to have a likely class, a possible class, and an unlikely class. And in the likely category, we have about 80% or so positive predictive value across classes. So 4 out of 5 times when we say something is there, it's there in the likely category. The possible is really meant to capture the higher sensitivity. So we propose those as possibilities for the radiologists to decide whether or not they're there. But they're definitely less confident than the likely category. And then we have the unlikely category where most of the things are. So there's utility here in triage, but also potentially in diagnosis. One of the questions that came up there was, well, if your model is so good, shouldn't you be able to find stuff that radiologists had missed in their initial read? And so we did this experiment to ask the question, did we find anything that the original radiologist had missed? And so I want to show you a few cases that resulted as a result of this analysis. This is a case of acute pancreatitis where the original radiologist had missed it, had described the pancreas as unremarkable, but our model was able to pick it up. In the second case, this one's an interesting one because typically coronary artery calcification may not be commented on in an abdomen pelvis scan, but sometimes it's included. And so the model is able to detect that and be able to present that as part of the report. And in this case, the radiologist had just said scattered plaque, but we were able to correctly call out the coronary artery calcification. Free air, especially when it's very small and subtle, can often be missed. And so here's a case of free air where the radiologist had originally noted no evidence of free fluid or free air that the model was able to pick up. So more recently, we've developed a2z2, and I just want to share some of the key capabilities of a2z2 right now. While that's loading, the main idea behind a2z2 was expanding the scope of findings from just 21 to as many as we could go with high accuracy. And so we ended up with a number of 140 findings. There are about 450 to 500 total findings in our analysis to detect, but we have the power and the ability to detect these 140 right now. And so it's across different organs and diseases. All right. So it's 140 findings which can be detected on Abdomen-Pelvis CT. One of the things that we added to our solution was the ability to quickly localize. So you can click on the findings and have it be localized in text. You can scroll up and down. And so the way we imagine the workflow is radiologists can scroll through, look at each one of the findings. If it's correct, and be able to mark it as correct. And that's a2z2. So now that we're able to do these 140 findings, one of the benefits of being able to do both the primary finding and the secondary complications is we can start to do something that starts to look a little magical. So I want to show you this demo, which looks at one of our newest features called Instant Prelims. So here we're able to take the findings and be able to generate these lines that can be localized in the image and be able to quickly be verified by the radiologist. This allows us to make the process of interpretation quick and have the review happen. And then you can just send out the report to be transferred over to a reporting software where another package can populate the full report and onto completion. So that's mainly what I wanted to share with you all today. I am happy to stick around or questions. If you want to connect with me on LinkedIn, here's the QR code. Thank you to CARPL for being wonderful partners over the years, and I look forward to our continued collaboration. So thank you.